Good afternoon, everyone. Delighted that you could join us. My name is Chris Doherty. I'm Vice President for Academic Affairs and Dean of the Faculty here at Chestnut Hill College. It's my pleasure to welcome Dr. Marie Mia Grogan, faculty member in English here at the college, and also the director of our interdisciplinary honors program. And Mia will speak a bit about the IDHP program here and also set a context for our speaker today. Thanks for joining us, and a pleasure to have you.
Other people walking around downstairs
Okay.
looking for you.
How are you? This is a chain of introductions because Chris is introducing me, and then I'm going to introduce Bob, who's going to introduce Dr. Alex Contasta. So I won't take much of your time. I just wanted to say welcome to everybody and welcome to Dr. Alex Contasta on behalf of the Interdisciplinary Honors Program, who's co-sponsoring today's lecture. So Interdisciplinary Honors Program, we're interested in bringing all different disciplines together to bear on subjects. And I had the pleasure of having lunch with Dr. Contasta, and I can tell you that she is a true model of interdisciplinary career path and life, and I hope she'll get a chance to tell you a little bit about it. I'll just, I know Bob Meyer will tell more about her background. I'll just say briefly, she did have an undergraduate double major, was it? Or
Major and minor.
Major and minor in French and philosophy. And then when you think about what she's going to be talking with us about today, you think, how did that happen? Hopefully she'll get a chance to share a little bit of that, maybe in the questions and answers or at some point. But I thank her for being with us and modeling, you know, a broad variety of interests. But I think Dr. Bob Meyer, professor of biology, will talk more about her more recent work. But welcome.
I'll try and be quick because I know these chains of introductions get tedious. David asked me to do this because he was afraid it would look a little too much like nepotism if he came up with it. I'm pleased to welcome Alex Contasta back. She's been here a couple of times already, I think, and given talks for us. I'll give you a little bit of her background, and then I'll shut up and sit down. So she has her BA from Villanova. Is the philosophy of the BA?
Yep.
The French, and the French is the minor.
Yep.
And philosophy and French. And then she wised up and got her master's in conservation biology. There's too many humanities people in here. Anyway, she got her master's from Antioch in conservation biology, and then went on to get a PhD from the University of New Hampshire in earth and environmental science. I'll give you a little bit of a blurb here, and this was written out better than I could ever write it out, so I'm going to read it to you. She's currently a research assistant professor at the University of New Hampshire's Earth Systems Research Center, and she studies winter ecology and winter to spring transition, especially the ways in which climate change impacts terrestrial ecosystems during these periods. She also explores interactions between land use and climate, with emphasis on carbon sequestration and greenhouse gas emissions from ecosystems under a variety of land uses and management regimes. So a lot of interesting stuff there. Today she's going to speak to us on the winter weather whiplash, and I think I'll let her tell you what that means.
Thank you. Thanks for having me. Can everybody hear me okay? Okay. So before I get into explaining what winter weather whiplash is, I just want to acknowledge all the people that are working on this project with me. This is very much a team science initiative, and it's also quite interdisciplinary. So we have economists, social scientists, educators on our team, as well as ecosystem ecologists like me. This is just a snapshot of some of us working on the project at an in-person meeting, but the list is a lot longer. I especially want to call out Nora Casson, who's the co-lead on this project with me at the University of Winnipeg. So thank you to all the people who are helping to make this work possible. Okay, so I want to start out with some definitions so that we know what we're all talking about when I am describing winter weather whiplash. And the first definition I want to get into is winter. What is winter? And this may seem like a little existential, and that's okay, because I have a philosophy degree, so I feel comfortable in that realm. But this actually came up because I do a lot of work asking stakeholders about what concerns them. In this particular instance, it's around changing winters. How are changing winters impacting you and what you do? So we're talking about foresters, we're talking about people who work in the winter recreation and sports industry, people who have maple sugaring operations. And we were having all these roundtables with people, and a recurring theme we were hearing was, why are you asking us about changing winters? Winter doesn't even exist anymore. What is it? You know, we're losing winter. And this really intrigued us. And so we kind of set out to try to define what winter was, to set some boundaries around the conditions that we were trying to describe. And so I thought I'd pose this question to you so you could think about this a little bit and see what you could come up with for a definition for winter. So anybody can shout out a definition that would like to. No raised hands necessary.
I guess you do it astronaut.
Oh, sorry, go ahead, Barb.
I was just gonna say, when the Earth is in a certain position.
Yeah, that's what I was gonna say.
Right?
You
So
can
that
do it
would,
astronomic.
right, that would be an astronomical definition, right? The position of the Earth relative to the sun. What else is winter? Yeah.
Very cold.
Very cold. Okay. Any other ways to describe it?
You could describe it romantically. I mean, it's a season of dark and light.
Right.
All that stuff.
Could be romantic, cultural. Right, so there's lots of different ways to describe it, and we hit on a lot of them. There's this astronomical definition, right? So it's the position of the Earth relative to the sun, the winter solstice, the vernal equinox. In the northern hemisphere, that's December 21st to about March 21st. The meteorological definition is the 3 coldest months of the year. In the northern hemisphere, that's December, January, February. You could have this cultural or romantic. I hadn't thought of that term before. It could be the ski season. It could be this time of darkness where we snuggle up and drink tea, whatever. It could be ecological, right? So in our part of the world where we have deciduous forests, the trees drop their leaves and a lot of plants and animals are dormant, right? There's lots of different ways to define winter. This is a cartoon that a colleague of mine found as a joke, and this is how we think of winter in New Hampshire, where it's this really big part of the year, and then there's this one day in March where it gets really warm and you get irrationally optimistic, and then it gets cold again. There's a tiny little slice of spring, a tiny little slice of fall, a little bit of summer when it's nice. But winter tends to last a long time, so we think about it a lot. But the definition that we came up with was really related to this idea that winter wasn't just the 3 coldest months of the year or the position of the Earth relative to the sun. It really has to do with it being cold, right? And this fits with this idea of what we call frigid winter. So frigid winter would be a period of sustained temperatures below freezing. So it's cold, and with those cold temperatures comes snow. And so that coldness and that snow cover together regulate ecological and biogeochemical processes and the services they provide to society. And this figure here is just showing how much snow there is on average in the northern hemisphere. So this is on the left, January. This is average snow cover extent across the northern hemisphere. And this is August, right? Half of the northern hemisphere is covered with snow on average historically because we have cold temperatures. And so this is this idea of frigid winter. It's not just December, January, February. That exists in Florida too, right? When we're talking about winter, we're talking about a specific set of conditions. And across Eastern North America, we're losing winter. So this is a figure from a paper that we recently published, and this is just showing our study area. All of these sites that are in red are losing cold days, days where it's below 0. And the size of the point is showing the strength of the trend. So bigger point means we're losing colder days, more cold days. The blue points indicate an increase in cold days, and the grays are no change. So overall, we're losing lots of cold days. You could put a same map up here for snow cover, and it would look very similar. So we're losing cold, and we're losing snow. We're losing frigid winter. But this is just describing average changes in climate. So this is a really nice schematic from Climate Central. They have lots of really cool infographics on climate change, and a lot of them are place-based, so you can go and look up where you're from and see how climate is changing in your area. But what this is showing is temperature, and these are these nice bell-shaped curves that would be showing the range of possible temperatures that might exist, maybe on Earth, right? We'll keep it simple. At the top here is average global temperature, and at these tails, these would be extreme cold and extreme hot. With climate change and overall warming, we see an overall trend towards increased temperature in the climate. So we're moving this curve to the right, and the average temperature is increasing. What we don't see in these average changes in climate are changes in extreme events. So an extreme weather event, another definition, is the occurrence of a weather variable above or below a threshold. So really, really warm or really, really cold, near the upper or lower range of the historical observations. So a really cold day would be here, extreme cold. A really hot day would be over here, extreme heat. And we've always had extreme events, right? These extreme events are not a sign of climate change by themselves because they've always existed. But climate change may increase the frequency of the events or the severity of the events, or both. And this is how this might play out. So this is a schematic from the Intergovernmental Panel on Climate Change Special Report on Extreme Events. I'm going to walk over here because I can't see it. So this on top is showing the same sort of bell-shaped curve I just showed. So this would be, average global temperature. At the top, we have our mean. At the tails, we have our extremes. With climate change, we may have a shift toward a warmer climate where the whole shape of the curve stays the same, it just shifts right. So that temperatures increase, the average temperatures increase, and we get more record warmth, but less record cold. Another way that climate might change and change the variability of extreme events is the second panel. So here, the shape of the curve is still symmetrical, but the tails get longer, right? So here now we see we have more cold weather and more hot weather. Another scenario is that we have our bell-shaped curve and it changes shape, and it gets less symmetrical. This example is showing that we have more record hot weather because of the asymmetry, and the cold weather stays the same, right? Scientists are trying to understand which way this is going now, right? But these are just the ways in which extreme weather events can change in frequency, depending on how the climate system changes. Okay, so we have extreme events, but there's also this concept of compound extremes. And compound extremes are extreme events that occur at the same time or one after another. So an extreme rainstorm followed by an extreme flood, followed by another extreme rainstorm. These multiple events that occur simultaneously or back to back. These multiple events, though, can also be not extreme themselves, but when you put them all together, they result in an extreme impact. And so this leads me to this idea of compound extremes and weather whiplash, another sort of definition. So given this idea of compound extremes and weather whiplash, what do you think weather whiplash would entail?
Sounds like going from one extreme to the other in a short period of time.
Yeah, exactly. Yep. So we're talking about compound extremes. So we know there's more than one, and it would be going from one to the other. You think about whiplash, you think about being in a car wreck and your head is going like this, right? So you're talking about a rapid back and forth change in conditions. And the first instance that I've seen of this term, weather whiplash, was actually in the popular media. This is a quote from Andrew Friedman from the Capital Weather Gang. It's a group of meteorologists who work out of Washington, D.C. And he defines weather whiplash as an ailment that strikes during or after an unusually rapid transition from one season to the next, such as when a work week starts out with temperatures in the low 40s and winds up in the 80s to near 90, thereby transitioning from winter to summer in a few short days and vice versa. So that's his definition. So as far as I know, the idea of weather whiplash started out in the media, but scientists have since picked it up. And the first instance that I know of the concept of weather whiplash in the scientific literature is from this paper from 2017 that talked about weather whiplash in agricultural regions. And in this case, they're talking about a sudden change between drought and flood. So this was a study that took place in the upper Midwest. In 2012, 2013, there was a big drought. Farmers, not knowing there was going to be a drought, planted their crops anyway. They applied fertilizer. The plants didn't grow because it was super dry. Then along come torrential rains. There are terrible floods. All the fertilizer that had been sitting there washes away into the Mississippi River, and there's terrible water quality problems. So here they're talking about drought to flood conditions. And I think this is an important point because often when we hear about extreme events, we're talking about some of the examples I have here. So extreme droughts, extreme floods, extreme precipitation events, heat waves. This is what I think is top of mind when a lot of people think of extreme events. And I would propose that less studied and less understood are extreme changes in winter weather events. So this is a figure from NASA Earth Observatory last January. So last January, if you remember, there was an extreme cold snap over the upper Midwest and a lot of Canada. This was a time when temperatures were minus 40 degrees C in some places. I have my Canadian colleague, Nora, my co-lead on this project. She was telling me that it was so cold they were canceling school in Canada, which like never happens there, for snow or coldness. So we have these extreme cold snaps, these extreme changes in winter weather that we don't understand as well. And I also would propose that we're increasingly living winter weather whiplash. So this is just a figure or a picture of a guy walking through Boston. This was in 2017, where the day after it was 50, 60 degrees outside, there was a foot of snow dropped across the New York to Boston corridor. So you go from something like spring to a blizzard in 2 days. And we're also seeing some climate scientists picking up this idea of weather whiplash. So winter weather whiplash is not just a term in the media, but it's also a term creeping its way into science. And so this paper by Judah Cohen talked about how changes in the jet stream might be affecting mid-latitude weather and setting us up for these whiplash events, lots of variability in the climate system because of changes in atmospheric circulation patterns. And so the goal of this project is really to try to get a better understanding of these winter weather whiplash events. What are they? How do we define them? Can we develop quantitative metrics for identifying them? And then how can we understand the impacts of these events on ecological systems, on social systems, and on coupled systems? Okay, so the first thing we set out to do as a team was to define these events. And I'm just going to skip to the chase and show you our definition. This is actually the result of lots of back and forth discussion and very much an agreed upon definition that had to result from a lot of consensus among a lot of different points of view. But this is how we're defining it. So winter weather whiplash is a class of extreme event in which a collision of unexpected conditions produces a forceful, rapid, back and forth change in winter weather and induces an unexpected impact on natural and/or human systems. And the areas that I have in bold and underlined are there to show that there are certain pieces of this that I think are really important. First, this unexpected conditions piece. So for winter weather whiplash to happen, we propose that it has to be extremely warm or rainy in the middle of winter, or extremely cold or snowy outside of winter. So you have to have anomalous warmth when it's supposed to be cold, or anomalous cold when it's supposed to be warm. This gets back to this idea of winter. What is winter, right? So we're talking about frigid winter. We're talking about conditions that are supposed to be cold, as in below zero, and supposed to have snow. And the impact depends upon the context in which the event occurs. If you have a really big precipitation event on soils that are already saturated, you're more likely to get a flood, right? So the antecedent conditions are important. If you have a really big rain event in February and it's over President's Weekend where the ski areas make a ton of money, that maybe matters a lot more than if it happens at the end of March when no one really cares and isn't thinking about skiing anymore. So context matters. Okay, so this is our conceptual model of winter weather whiplash. We're big on these conceptual models. And so I'm just going to talk about this really briefly and then show you some examples that are a little bit more tangible and less abstract. So here we have the context of the system. We have the natural system context. Are the soils really wet? Are there leaves on the trees? We have the human system context. Is it President's Weekend? And a lot of people are thinking about skiing. And on top of this natural or human system context, we have this synoptic weather event. And by that, I mean a big weather event that covers like over 1,000 kilometers, right? We're not talking about a little thunderstorm. We're talking about a big event. And it interacts with this natural and human system context to create the event. Is it rain on snow? Is it a really anomalous winter warming event? And that event is going to have impacts on the natural system. Do a lot of trees come down? Is there a lot of flooding? On the human system, do ski areas lose a lot of money? Do people's power lines go down? Are their basements flooding? And those impacts can lead to some reorganization in the human system or the natural system. If a lot of trees come down, does that mean that we change regulations about how trees have to be trimmed so they don't interfere with power lines? In the natural system, if a lot of trees come down, does that open up canopy gaps and allow seedlings to grow? Or does it make trees more vulnerable to pests, right? There can be lots of sort of feedbacks embedded in the system. So that's our conceptual model of winter weather whiplash. But I'm going to give an example that sort of plays out what it looks like in a real event that happened within my memory and hopefully within the memory of a lot of people here. So I want to talk about the Snowtober of 2011. Bob was just asking me about this, like weather whiplash, do you mean like that big Halloween snowstorm? And I'm like, yes, I do. So this is an example of a winter weather whiplash event outside of winter, when it was cold and snowy when it wasn't supposed to be. How many students remember this event? Couple? Yeah? Yeah, I'm guessing, depending on how old you were, you might have been 10, 11, 12, 13 when this happened, right? Okay, so this was a big deal for a lot of kids at the time. Okay, so here's the event. Synoptic weather system. We have low pressure that forms off the east coast and converges with cold air outside of Canada. So we have lots of moisture in the air that mixes with cold air coming out of Canada, and then it can snow a lot, right? This is a nor'easter type event. You can see this is just a satellite photo of some of the impact area the day after it happened, and you can see how green some of the surface is with snow on top, right? So it kind of gives you an idea already of what we're setting ourselves up for. In terms of the natural system context, there were leaves still in the trees. It was October 29th, October 30th. Depending on where you were, further south, this was a bigger problem, especially in areas where the trees were mostly oak or beech, because those trees are more marcescent. They hold onto their leaves longer. They don't senesce as early. And so even if those leaves were already changed and mostly dead, they're still sitting on the trees. Another thing to keep in mind was that the ground was already saturated. There had been a lot of rain. So you have trees that still have leaves and the ground is wet. Human system context. There had already been big power outages in recent memory. Hurricane Irene was in August of that year, and there was a tornado outbreak between, I think it was Massachusetts and Maine in June of that year. So people had already lost power a couple times and for a while before this happened. Another thing to keep in mind is that the plow and salt trucks aren't ready for a snowstorm, right? So there's like a lot of things that are kind of setting us up for a bad situation. So we have this event. We have an early nor'easter. It dumps 32 inches of snow in some places. There's widespread tree mortality due to the weight of wet snow on trees and leaf, especially trees that were oak or beech. This is actually a picture of one of the co-authors in this project, John Campbell. This is his parents' house in New Jersey a couple days after the event happened and the snow had already melted. You can see an oak tree in the front that had fallen over. So lots of trees down, lots of vegetation mortality. This can lead to vulnerability to pests and diseases, impacts on wildlife habitat. When you have all this litter coming into the system at once, all this woody litter, it can change nutrient cycling in the forest. Human system impacts, over 3 million homes and businesses lost power. Halloween was canceled, and I think this is why it really sticks in the minds of people who were in their early 20s now, because we may think, not a big deal compared to people losing power, but if you're a kid and it's the biggest candy holiday of the year, and this happened on a Friday, so you're thinking, I'm gonna get my candy and eat it all weekend, and it didn't happen, you're gonna remember this, right? So that would be a human system impact. And then some of the sort of system reorganization responses, the combination of this and the outages from past events, from Irene and these tornadoes, led to new utility rules for tree trimming, especially for Eversource, which is a utility in Connecticut that just got slammed. This really bad PR, and they had to change a lot of the ways that they did things because of this. So that's one example that shows the entire conceptual model. I'm just going to show a few other ones that don't go through the entire thing for the sake of time, but hopefully to give you an idea of what we're talking about. So this is another example, the fall spring of 2012, another winter weather whiplash event outside of winter, when it was really cold when it wasn't supposed to be. In this example, there was an early leaf out due to record-breaking high temperatures in March. So this panel here is showing the anomalies, like how early leaf out happened across the continental United States. And points that are in red and orange is where leaf out happened really early because it had been warm really early. Then, after all these new leaves emerged and were still sort of tender and vulnerable, we get this spring frost that damaged a lot of the plant tissues. This resulted in billions of dollars in economic losses, especially for fruit crops, for orchard species like apples, peaches. But even in forests, you can have reduced photosynthesis, reduced carbon uptake for the entire year, because after that first flush happened and that initial vegetation experienced mortality, the trees never fully recovered, right? And they weren't able to photosynthesize and take up as much carbon dioxide out of the atmosphere for that entire year. So that would be an example of a natural system impact. Okay, this example, the winter heat wave of 2017, this is an event that happens during winter, and these are the kinds of things that we've been experiencing this winter, the last few years, kind of top of mind for a lot of us. So this is a picture from one of our local research sites in Durham, New Hampshire, and this is not in late March or early April, when you would expect to see snowmelt happening in our part of the world. This is in late February. This was the warmest February ever recorded. This is a picture from the Boston Globe of people walking around. This mom is wearing shorts. They're buying hot dogs. People were doing yoga on the docks in Boston. It was 70 degrees, right, in late February during this period. So really anomalous warmth. The impacts of this event can be major economic losses for winter recreation and tourism. People don't think to go skiing if it's really warm outside, and the ski areas themselves may not have snow. There's also potential losses of life, right? There's lots of ice fishing in New England, in the upper Midwest, and Canada, and the ice gets thin and people fall through. There was a really bad ice climbing accident in January in New Hampshire in the White Mountains when we had those 2 back-to-back days of anomalous warmth where these ice floes just fell on these climbers' heads. And they walked away okay, but it was really scary. So there can be, potential losses of life from these. Rapid melt can also lead to flooding. Really bad flooding, in fact, because rivers may not be flowing fast enough, and there can be lots of ice jams and really terrible flooding set up from these anomalous warmth events. And rapid warming can cause soils to start getting active because they're not frozen anymore. They start breathing, they start releasing carbon, all the microbes in there start breathing into the atmosphere. And if one of these frost warming events is followed by a frost event, you can lead to all kinds of other impacts. Deeper soil frost, all those animals that like to burrow in the soil beneath the snow can experience all kinds of problems. So just an example of an event within winter where you have anomalous warming. And you can couple anomalous warming with precipitation and you get rain on snow. So there was an event in 2016 in northern Vermont and southern Quebec where rainfall of over 2 inches fell within a day on top of a big snowpack. And then you have, again, localized flooding, ice jams. The other thing that can happen with these is that you have impacts on water quality. You have huge pulses of nutrients leaving watersheds. And once they leave upland systems and get into surface water, they can act as pollutants. So this would be another event of a winter weather whiplash situation occurring within winter, warmth when it's not supposed to be warm. And so these types of events and our definition sort of led us to develop this typology of winter weather whiplash. So here we have, within winter, these sort of normal winter conditions. And again, by that we mean frigid winter. It's supposed to be cold, it's supposed to be snowy. But instead, what we get are potentially these heat waves or these rain on snow events, and those happen within winter. Or we can have conditions outside of winter when it's supposed to be warm. You see the greenness of the vegetation. And during this period, we can have extreme cold snaps or we can have snowstorms. And so those are our 4 types of events, these cold snaps, these snowstorms that happen outside of winter, or these heat waves or rain on snow events that happen inside winter. But the thing they share in common is that they all are involving the crossing of this 0-degree threshold, right? So we also propose that one of the hardest physical thresholds in nature is the freezing point of water. And if you get above that, water melts, snow melts. If you get below that, water freezes. And that can really set up the system to have to experience big impacts if you're sort of crossing that threshold a lot of times, especially when you're not supposed to be. Okay, so we have these definitions of winter weather whiplash. How do we then take those and develop quantitative metrics for identifying events? So what we did as an initial attempt for this was that we used the Hubbard Brook Ecosystem Study as a model system. So Hubbard Brook is here. It's located in the White Mountains of New Hampshire. It's one of the longest ecological observatories in the world. It has a hydroclimatic record of air temperature, precipitation, snowpack, and stream flow that goes back to the 1950s. So it's got this really long record that we can use. And they also are monitoring vegetation and when vegetation goes through bud burst and leaf out and when leaves start to change in the fall. We need to know that because some events happen outside of winter. And so we took advantage of this record as a way to try to develop a quantitative metric of winter weather whiplash events using a fairly small data set. Just as a little sidebar, vegetation phenology, because this ends up being a big deal for winter weather whiplash. Vegetation phenology basically is seasonal plant life cycle events, and they're usually described with indices. When was the first day of bud burst, of flowering? When did leaves expand, and when did they change color and fall off of the trees? Often phenology is detected by looking at vegetation greenness. How green is the vegetation? And you can do that from the ground, as just by looking at it. You can use cameras. That's what these things are here. You can also look at greenness from space using satellites. And again, for winter weather whiplash, we need to know phenology because some events impact vegetation. And then we borrowed an approach for identifying extreme weather events from the sort of extreme weather literature using this threshold-based approach. So this, again, is our nice sort of bell-shaped curve, kind of like what I showed before. This would be daily average temperatures. I think this is a place in Australia. The top here would be average or sort of median conditions that you might expect. If you're below the 5th percentile, then you would be considered to have, cooler weather, like extremely cooler weather than what is typical for that time of year. If you're above the 95th percentile, then you would have an extreme warmth event, right? So the way that the extremes literature often identifies events is by saying, okay, how anomalous was it? How much below, the 5th percentile or how much above the 95th percentile was it compared to the historical baseline conditions? And so we kind of borrowed that approach, but we don't know what's extreme, right? Like we don't know what an extreme winter weather whiplash event is. So we thought, okay, we'll determine what the range of conditions have been at Hubbard Brook, and then we'll say, okay, when did the system cross the 1st percentile, the 5th percentile, the 10th, the 90th, the 95th? We'll allow our criteria to be really conservative or really liberal, and see like how many events can we detect, right? Because we didn't know what we might be able to pull up. So we'll flag instances where conditions of snow and vegetation and temperature cross these percentiles. We also recognize that there may be hard physical thresholds in nature that incite events, regardless of how warm or cold something was compared to historically. Like there may be a really defined amount of snow that has to be falling on a really defined amount of leaf for a tree to come down, right? So we also try to find hard thresholds in nature that we scoured the literature for to flag events that met those conditions. And this is what we got. So this is a figure that we call our rainbow plot, just because there's lots of colors in it. It's pretty data rich, so I'm just going to step through it. What you're seeing is each of the 4 events that I talked about: the 2011 Snowtober Halloween snowstorm, the fall spring of 2012, the 2016 rain on snow event, and the 2017 winter heat wave. The x-axis is showing the day of year. Often in ecology, we don't say it was January 1st, we say it's day of year 1. And we deliberately have winter in the middle of this graph and the growing season on the sides to kind of highlight the middle of the winter period. Then there's lots of y-axes. There's air temperature, there's the phenology index, there's how much snow water equivalent was there, there's rainfall or snowfall precipitation. And what you see, and I'm going to go through temperature as an example, there's this red band on each of these graphs. And this is showing the range of potential temperatures for each of those days a year for the entire record at Hubbard Brook, between the 10th and the 90th percentile. This is how cold it was for a maximum temperature on that day of year, and this is how warm it was at the top. And then the dark line is showing for that actual year what the maximum temperatures were. So you can see when that line crosses that upper threshold, then you get a dot, you get an event happening, right? You get an anomalous warmth. And so you can sort of look at each of these different bands of color and infer the same thing. So the orange one is daily minimum temperature, the range of those conditions. This blue line is the range of potential snow depths. This green line is the range of potential phenology conditions. Here, it's a phenology index that is corresponding to, events like bud break and leaf expansion and so on. But what we did was that we highlighted in the square dots each time the conditions crossed the 90th percentile threshold, or these triangles each time across whatever hard literature value we came up with. And we looked at these and said, great, we're able to detect events. Here is our Halloween Snowtober snowstorm. We can pick this up with our quantitative way of trying to detect this. Here's our fall spring of 2012. We were able to pick this up. Here's our rain on snow event. There was another one here. That wasn't, something that we were aware of, but here's our rain on snow event, and here's our winter heat wave, right? So they work, right? Sort of. So that's pretty satisfying. But that's just one site. So our next step is to try to take this out for a spin across northeastern North America. So now we're expanding the same approach across a much bigger spatial area. And here we're using the Global Historical Climatology Network. So these are weather stations across the study domain that have been measuring daily total precipitation, snowfall, snow depth, and temperature for different amounts of time. Some of them have only been going for about 30 years. Some of them have been going for 90 years. We wanted at least 30 years, which is considered a climate normal, because we think these events are pretty rare. So to be able to pick them up, we want to have a long enough period of time to see if we can even find them. And so these points are just showing where the stations are and how many years they have. Areas that are darker have more years. So we had to do a lot of things to the data before we're ready to apply our winter weather whiplash metrics. First, we have to actually model snow depth. This is a huge problem in the eastern United States. We have really poor snow records. The western US does a way better job, which makes sense because they rely on snow for their water, and we don't. So even though we measure snow, it's pretty intermittent. You never know if a zero is because it was really zero or because somebody actually didn't measure it that day. So I always say, be a hero, record the zero, right, for posterity. And so we had to actually model this. And so we did this with a really simple degree day snow model. So we know what temperature is, we know what precipitation is, and we can model snowpack by saying, okay, we know that snow is going to fall between -2 and 2 degrees Celsius. We know that snow might melt at the same range, and we know a melt rate might be 1 to 6 millimeters per degree C per day. We can run a big model with lots of parameter combinations and pick the best fit, like where does observations best meet our predictions. And so we model snowfall. The other thing we have to do is model vegetation phenology, because again, we need to know what state the vegetation is in to detect an event. And these weather stations aren't measuring that. So we use this modeling package called PhenoR with PhenoCam data. So these are these cameras that take pictures of vegetation canopies. They're basically security cameras that people put up above the canopy. And they seriously, we have some of these. You order them from the same company that you would if you were trying to monitor your drugstore for shoplifting. And so they're taking pictures every day, usually in the middle of the day, and tracking vegetation greenness over time. And so you can take the greenness in an image and you can infer different phenophases. When is bud break? When is the maximum rate of leaf expansion? When does the canopy close? When does it start to change color? When are half the leaves off? When does senescence happen? So you can pull that greenness information out of the phenocams and estimate phenophases of vegetation. And then you can relate those things to temperature. So you might have a really simple model of temperature and the day of year when vegetation started to change color. That's this example. And you can use the model parameters to estimate vegetation phenology where you don't know those things. So we have these weather stations where they're not measuring this stuff, especially if it was 90 years ago. You know what temperature is, you know X. You can take this model equation and predict Y, right? So we did that. But it gets a little bit more complicated because these stations are scattered across a big area that has different types of land cover. So you have evergreen needleleaf, deciduous broadleaf, mixed forests, croplands, urban areas. So this is just showing what land cover is across that study area. Where our stations are, those are the yellow points, and then the colored points are where the phenocams are located. So we can do all this, but we do it by land cover and associate each station with the land cover. And get, for any given station, this is what the greenness was over the course of a year. So we do all that. We have our weather station data. We simulate snowfall and snowpack. We simulate greenness. And now we can apply our same metrics to detect winter weather whiplash events. And so this is an example of what we get, another really data-rich slide. But here we have our study area. And each of these panels is one of our 4 types of events. We have rain on snow. We have our snow on leaf or our early or late snowstorms. We have these cold on leaf for spring frost events, or we have our winter heat waves. Here, the size of the dot indicates how many events happened at that station within a 30-year period from 1988 to 2018. So bigger dots mean more events. Smaller dots mean less events. And what we're looking for as a first pass for this analysis is, are we seeing patterns? Like it looks like there's kind of a lot of these frost events in the upper Midwest. It also looks like for rain on snow, there's sort of like a band of latitude here where these events tend to happen more than further north or further south. And that makes sense because you have to have conditions where it's cold enough to snow some of the time, but warm enough to rain some of the time. So if you're too far south, you don't get snow, and if you're too far north, you don't get rain. These are hypotheses, right? So we're just starting to look at this. But what we're asking is there a strike zone for winter weather whiplash events where we're seeing these events happening more frequently and maybe where they be more likely to occur in the future? And so next steps for this, right now we're expanding our study domain for all of Eastern North America below the boreal forest zone. So we're going to go, it'll be mid-Atlantic and a little bit further south. We'll look at change through space and time. So do we see spatial patterns, and also are we seeing changes in the frequency of these events? We also are trying to understand what are the underlying atmospheric circulation conditions that drive events. I have a new colleague who's working on that. And can we predict the future frequency of winter weather whiplash events? So can we use what we know about the past to infer what might happen in the future? Last, impacts. So how do we understand impacts of these events on ecological, social, and coupled systems? So I'm just going to show you one example of our very sad snowman here. How do rain on snow events and winter heat waves affect stream flow? So here we're working in a few different study sites. This is Hubbard Brook again, Sleepers River. This is Biscuit Brook down in the Catskills, and then the Experimental Lakes area in Western Ontario. So we're working in 4 different catchments. They are of different sizes. They have different mean winter temperatures. We have warmer temperatures at Biscuit Brook and Hubbard Brook, colder temperatures at the Experimental Lakes, and then different amounts of total winter precipitation. We can apply our winter weather whiplash event criteria to identify these events that have happened in these catchments. And so this is what we get. So these are our 4 different areas: Experimental Lakes in Ontario, or in in Ontario, Biscuit Brook in the Catskills, Sleepers River in Vermont, Hubbard Brook in New Hampshire. The x-axis here is showing average daily flow. And just note that the scale of the x-axis is exponential, right? So you go from 0.1 millimeters to 10 to 1 to 10 to 100. And then what you're seeing, again, are these curves, right? Similar to what you've seen already. So the curves are showing the average distribution of flows for 3 different types of events. The green is normal. There's no winter weather whiplash. The orange is a winter heat wave, just anomalous warmth, but no precipitation. The blue is rain on snow. And in all cases, what you see is that where there's rain on snow, those curves are shifted to the right. So you're seeing higher flows associated with these rain on snow events. Higher flows on average, and then also higher flows at the long tail of the distribution. So more extreme flows. So these events lead to bigger flows in these systems. The other way to look at this is how many of these events are associated with the highest flows of the year. In snow-dominated ecosystems, the biggest flows occur during spring melt, it's spring freshet. And so what this is showing is our 4 catchments, our 2 different types of event, and the number of times that the event, like a rain on snow event, caused the maximum flow of the year. So 6 times at Sleepers River, a rain on snow event caused the maximum flow of the year, not the spring freshet. So you're really messing with the hydrology of the ecosystem in that case. The next thing we're doing with this is trying to see how does that impact stream water quality, having these big flows out of season and solute export from these systems. How do they impact downstream ecosystems and communities? What are some of the social impacts as well? And then we also are going to be looking at impacts of other winter weather whiplash events like our snow on leaf events and our fall springs. What are the impacts of those? One thing we can do with the rain on snow events, we are using the Spatial Hazards and Events Losses Database for the US, the SHELDAS. It's kind of a mouthful. This gives county by county information of the impact of events across the United States. And so we can look at the counties surrounding these catchments and see for any given event what was the total economic cost associated with that, usually from a presidential disaster declaration. But we can start to make a first pass at looking at the economic impacts that way. And ultimately, we're really interested in these events, these winter weather whiplash events or these extreme events that consist of unexpected conditions that produce a forceful, rapid back and forth change in winter weather and cause impacts on natural and human systems. We really want to understand these events better and the extent of their impacts to try to minimize their risks. And we're really at the beginning of what I hope is a many-year research collaborative that does that. We're trying to quantify the frequency and severity of these events across Eastern North America and trying to understand their impacts on coupled natural and human systems, focusing on events that occur but within frigid winter and outside of frigid winter. And that's it. So thank you again to my collaborators.